Have you ever, stared at a huge pile of notes for a big test and just wished someone could point you straight to what really matters?
Yeah, cut through the noise.
Exactly. Well, today, consider us your guides for exactly that. Welcome to the deep dive. We're here to get you well informed without drowning you in details.
That's the plan. And for this deep dive, we're tackling Chapter 19 from the official SAT study guide. It's called Additional Topics in Math.
Sounds a bit vague. Additional topics.
It does, but it actually covers a very specific, critical chunk of the SAT math test. It's smaller, maybe, but really important.
Okay, so what are we covering? We're going to unpack everything, right? The essential skills, the strategies you need, the kinds of questions you'll definitely see.
We'll walk through the official examples, share those key tips, basically everything on geometry, coordinate geometry, trigonometry, and complex numbers.
And our promise to you listening is that this will be focused, hopefully engaging, and really designed to give you the insights for test day success without the overwhelm.
Definitely. And it's important to know these topics altogether, they make up about 10% of the math questions. That's roughly 5 or 6 questions out of 58.
Okay, not a huge percentage, but...
But they pop up in both the calculator and no calculator sections, so you really have to know your stuff. And honestly, they can be some of the trickier ones. Nailing these can give you a real edge.
All right, then. Let's dive in. Where do we start with these additional topics?
Okay, first start is geometry. This is probably the most familiar territory for many students. It covers lines, angles, triangles, circles, the shapes.
Standard high school stuff.
Pretty much. Plus area, surface area, and volume calculations.
Now, here's something really important, maybe even a bit of a relief for test takers. The guide points this out clearly.
Oh, yeah. This is huge. You do not need to have a giant list of geometry formulas memorized.
Right. They actually give them to you. They're right there in the reference info at the start of each math section.
Exactly. So the test isn't really about can you memorize a formula. It's about can you figure out which formula to use and how to apply it to the problem in front of you.
It's about problem-solving agility, using the tools they give you. So, if you're stuck...
Glance at that reference sheet. It's surprising how often students forget it's there. It's like a built-in safety net.
Okay, so formulas provided. But you still need some background knowledge, right?
Oh, absolutely. You need those basic geometric definitions you learned. What parallel lines mean, what perpendicular means, congruent versus similar triangles, that kind of thing.
And the notation, too, I guess, like the symbols for angles or parallel lines.
Yep. Basic geometric notation is key to even understanding the diagrams and the questions sometimes. Without that foundation, the formulas won't help much.
Makes sense. So let's break down geometry a bit further. What about lines and angles?
Okay, so for lines and angles, you need to be comfortable with concepts like segment lengths, finding midpoints, angle measures, obviously.
And specific types of angles.
Right. Vertical angles, remember the X shape, opposite angles are equal. Angle addition, knowing angles on a straight line add up to 180 degrees.
And all the angles around a single point add up to 360.
Exactly. And then a big one. Parallel lines cut by a transversal. You need to know about alternate interior angles, corresponding angles, all those relationships. They come up a lot.
Okay, from lines and angles, we naturally move to shapes, triangles, and other polygons.
Yes. Triangles are huge on the SAT. Especially right triangles. You absolutely need the Pythagorean theorem. A plus B plus B equal, it's everywhere.
Can't escape Pythagoras.
Never. Also know the properties of equilateral triangles, all sides angles equal, and isosceles triangles, two sides angles equal. And definitely know your special right triangles.
The 30-60-90 and the 45-45-90.
Knowing those side ratios, like 143.2 for 30-60-90 and 1.1, SUT2 for 45-45-90, is a massive time saver. It lets you skip calculations.
Good tip. What else was triangles?
You need to know the difference between congruent triangles, identical shape and size, and similar triangles.
Similar means same shape, different size.
Exactly. Corresponding angles are equal, but corresponding sides are proportional. You'll use ratios with similar triangles. Oh, and the triangle inequality theorem. Any two sides of a triangle added together must be longer than the third side.
Seems basic, but probably useful for eliminating impossible answer choices.
It can be. Then we also have other polygons. Squares, rectangles, parallelograms, trapezoids. Knowing their specific properties is important. And regular polygons, too.
Okay, moving on to circles. What's key here?
Well, the basics first. Radius, diameter, circumference, which is 2 core or MIDI. But the SAT really loves testing angles and arcs.
Right, you mentioned this earlier, central angles versus inscribed angles.
Yes. A central angle's measure is equal to the measure of its intercepted arc, but an inscribed angle where the vertex is on the circle is only half the measure of its intercepted arc. That distinction is crucial.
Got it. Half for inscribed, equal for central.
You'll also need to calculate arc length and the area of sectors. Think of them as like the crust length and the area of a pizza slice.
Good analogy. Anything else on circles?
Maybe a little bit about tangents, lines that touch the circle at one point, and chords, lines connecting 2 points on the circle.
Okay. And the last bit of geometry is area and volume.
Yep. This involves applying formulas, usually from the reference sheet, to find the area of flat shapes or the volume, and sometimes surface area of 3D solids like cubes, cylinders, or prisms.
The challenge here is probably just picking the right formula and maybe breaking down weird shapes.
Exactly. Sometimes you need to subtract the area of one shape from another or add volumes together.
Let's make this concrete with some example strategies the guide mentions. Like example 1 often involves parallel lines.
Right. A common setup is parallel lines with a transversal cutting through, forming triangles. The key strategy is usually spotting similar triangles.
Ah, so you use those proportional side ratios we talked about.
Precisely. You set up a ratio to find a missing side, and maybe then use the Pythagorean theorem if there's a right triangle involved too. The guide reminds you to practice these on sappractice.org.
Good reminder. What about example 2 with regular polygons? Like a 9-sided figure, a non-infargon.
Yeah, finding angles in regular polygons. The insight there is often to draw lines from the center to each vertex. This creates a bunch of identical isosceles triangles.
Okay.
And since all the angles around the center must add up to 360 degrees, you can find the central angle of each triangle, 360 divided by the number of sides. Then use the fact that it's an isosceles triangle to find the other angles.
Clever. Breaking it down. Example 3. Circles again.
Usually inscribed angles, the aha moment is just remembering that rule. The inscribed angle is half its intercepted arc. If you know that, the problem often just solves itself.
Simple rule, big impact. Example 4 often has tangents.
Tangents to circles. The absolute key principle. A tangent line is always perpendicular to the radius at the point where it touches the circle.
Okay, so that creates a right angle.
Exactly. It often forms a hidden right triangle, maybe even a 30-60-90 triangle. You might then need to combine that with finding the area of a sector to calculate some weird shaded region.
Lots of combining concepts. How about example 5, trapezoids, parallelograms?
Yeah, for those, you need to use their specific properties, like opposite sides are parallel in a parallelogram, or the formula for the area of a trapezoid. Often you'll need to draw an extra line, like an altitude, which again creates a right triangle. Maybe a 45, 45, 90 this time.
Seeing a pattern here with the special right triangles.
They love them. And finally, example 6 might be about volume, like a glass vase being filled with water.
Calculating remaining volume, perhaps.
Yeah, or how much water fits. It's usually about applying the volume formula correctly. But here is a general tip that applies to many geometry problems, especially this one. Pay attention if it says, figure not drawn to scale.
Ah, right. Means you can't just eyeball it. You have to rely purely on the numbers and formulas.
Exactly. Don't trust your eyes, trust the math.
Okay, that's a solid run-through of geometry. Now, where do we go next? Putting shapes on a grid.
Precisely. We shift to coordinate geometry. This is where algebra and geometry meet. We use equations to describe shapes on the xy plane.
So, familiarity with the coordinate plane is step 1. Plotting points, x, y. Understanding positive-negative directions.
Right, the basics. But the really big SAT topic within coordinate geometry is the equation of a circle.
Okay, this one sounds important.
It is. You need to know the standard form. XA plus YB plus RR, RR. Memorize this.
And what do the letters mean again?
AB is the coordinate pair for the center of the circle, and R is the radius. If you know this template, you can pull the center and radius straight from the equation or write the equation if you know the center and radius.
Makes sense. How might they test this? Example 7 involves moving a circle.
Yeah, translating a circle. If you slide the circle, say, 3 units right and 2 units down, how does the equation change?
Well, the center, AB, changes, so you just adjust the A and B values in the equation.
Exactly. It's pretty straightforward if you understand the standard form.
And what about example 8? This one sounds a bit more algebraic. Completing the square.
Ah, yes, this is a critical skill. Sometimes they give you the circle equation all jumbled up, like x up plus 4x plus y6y equals 12. It doesn't look like the standard form.
Okay, so you have to rearrange it.
You have to use a technique called completing the square. You group the x terms, group the y terms, and then figure out what number you need to add to each group to make it a perfect square trinomial, something that factors neatly into xa or yb.
Like for x up plus 4x, you'd add 4 to make x plus 2.
Precisely. And whatever you add to the left side, you have to add to the right side to keep the equation balanced. Once you do that, the equation magically transforms into the standard form, and boom, you can see the center and radius.
So mastering completing the square is really key for these circle problems.
Absolutely essential. It comes up often.
Okay, circles on the grid, checked. What's next? Angles and triangles again, but with a twist.
Sort of. We move to trigonometry and radians. Trigonometry studies the relationship between angles and side lengths, mainly in right triangles.
And radians.
Radians are just another way to measure angles instead of degrees, kind of like using Celsius instead of Fahrenheit.
Got it. Let's start with the right triangle trigonometry. Is this SOHCHTOA time?
It is indeed. SOHCAHTOA is your best friend here. Sine, SOH, is opposite side over hypotenuse. Cosine, CAH, is adjacent side over hypotenuse. Tangent, TOA, is opposite side over adjacent side.
You just have to correctly identify which side is opposite the angle, which is adjacent next to it, but not the hypotenuse, and which is the hypotenuse opposite the right angle.
Nailed it. If you can label the sides correctly relative to the angle you care about, and you remember SOHCHTOA, you can find missing sides or set up equations.
Is there anything else crucial for basic trig?
Yes, there's a very useful identity. The complementary angle relationship. It says that sin x degrees equals cos, 90 degrees x degrees.
Meaning the sine of an angle equals the cosine of the angle that adds up to 90 degrees with it.
Exactly. Sine and cosine are cofunctions. If you see sin 30 degrees, you know it must be equal to cos 60 degrees. This can be a neat shortcut on some problems.
Okay, good one to remember. Now, about radians. Why do we need another way to measure angles?
Well, radians are often preferred in higher math and physics because they relate angle measure directly to arc length and radius in a very clean way. They're based on the radius of the circle itself.
How do we convert? Is there a simple way?
The key conversion factor is radians equals 180 degrees. If you remember that, you can convert back and forth using ratios, like 90 degrees is 2 radians, 45 degrees is 4 radians, and so on.
So you might need to convert degrees to radians or vice versa, depending on the question.
Yes, sometimes, especially when dealing with certain formulas.
You mentioned the unit circle. How does that fit in with radians and trig?
The unit circle is a fantastic concept. It's a circle with a radius of 1, centered at the origin, 0, 0. If you draw an angle in standard position, starting on the positive x-axis, rotating counterclockwise,
Okay.
the point where the terminal side of that angle hits the circle has coordinates, x, y. And here's the magic. On the unit circle, x is equal to the cosine of the angle, and y is equal to the sine of the angle.
Whoa, so the coordinates are the cosine and sine values.
Exactly. Cos thing the plane. It visually connects trig ratios to the coordinate plane. It's especially useful for understanding trig values for angles beyond 90 degrees or negative angles.
That's powerful. And what about arc length? You mentioned radians are important here.
Yes, the formula for arc length is S what, where S is the arc length, or is the radius, and S is the central angle. But, and this is critical, the angle must be in radians for this formula to work.
Ah, okay. If they give you the angle in degrees, you have to convert it to radians first before using S-revat.
Absolutely. That's a classic SAT trap.
Let's look at the examples. Example 9 sounds like basic trig.
Yeah, it probably gives you a right triangle with some side lengths and asks for, say, the sine of one of the angles, or maybe uses similar triangles and trig ratios together. It's about applying SOHTHO correctly.
Straightforward application. Example 10 involves the unit circle.
It might give you the coordinates of a point on the unit circle, maybe a coordinates related to a 45, 45, 90 triangle like 22, 22, and ask for the angle in radians.
So you'd recognize that point corresponds to 45 degrees, which is 4 radians.
Exactly. It tests if you can connect the coordinate geometry, the special triangles, and the radian measures.
And example 11, complementary angles again.
Likely, but maybe using radians this time. Like if they tell you sin x, cosy, and x and y are acute angles in radians, you should know that x plus y must equal 2, which is 90 degrees.
So that sin x degrees cos 90 degrees x degrees relationship becomes sin x equals 2x in radians.
Perfect. It shows how these identities work in both systems. Knowing this can lead to a quick solution, maybe finding the value of some constant like k if they set it up as an x, cos kx.
Okay, trig and radians covered. We're down to the last additional topic. What is it?
The final section is on complex numbers. These often seem a bit strange at first because they involve the imaginary unit I.
Right, I. What is I again?
I is defined as the square root of -1. So I is as 1 by. This allows us to take square roots of negative number.
And the crucial property.
The most important thing to remember is that if I are 1, then I arise a -1. This single fact is the key to simplifying almost all complex number operations. Anytime you get an I, just replace it with -1.
Okay, I equals 1. Got it. How are complex numbers usually written?
They're written in the standard form a plus by. A is the real part, or regular number, and b is the imaginary part, the part multiplied by I. So 3 plus 2i is a complex number. Real part 3, imaginary part 2.
How do we do math with these, like addition and subtraction?
That's the easy part. You just combine the real parts together and the imaginary parts together, like combining like terms in algebra.
So 3 plus 2i plus 1 4i would be 3 plus 1 plus 2 to 4i.
Exactly. Which simplifies to 4 2i. Treat I like a variable for adding and subtracting.
Okay, what about multiplication?
For multiplication, you usually use the FOIL method, just like multiplying two binomials. For example, 3 plus 2i, 1 4i.
First, outer, inner, last.
Right, so 3 1 plus 3 per 4i plus 2i 1 plus 2i and a half of 4i. That gives you 3 12i plus 2i 8i by I.
And there's the I.
Yep, now you replace I war with an F1. So that neganek I war becomes an F at 1, which is plus 8.
Okay, so we have 3 12i plus 2i plus 8.
Now combine the real parts. 3 plus 8 equals 11, and the imaginary parts,
Yes.
negative 12i plus 2i plus 2i plus 10i. The final answer is 11 10i.
Got it. FOIL, then substitute I into 1, then simplify. What about the trickiest one, division, as in example 12?
Division involves a special trick using the conjugate. The conjugate of a complex number, a plus by, is just a by. You flip the sign of the imaginary part
Okay, why do we need the conjugate?
to get the I out of the denominator. If you have a fraction like 3 plus 2i, 1 4i, you multiply both the top and the bottom by the conjugate of the denominator.
So multiply top and bottom by 1 plus 4i.
Yes, exactly. When you multiply 1 4i by its conjugate, 1 plus 4i in the denominator, the I terms will cancel out thanks to that arithmetic 1 property, leaving you with just a real number downstairs.
And then you just multiply out the top using FOIL like before and simplify the whole thing into the standard A plus by form.
That's the process. It looks complicated, but it's systematic. Multiply top and bottom by the conjugate of the bottom, simplify both, and you're there.
So the practical advice here is treat I like a variable, always remember I into worlds equals 1, and for division, use the conjugate.
That's pretty much it. Complex numbers are consistent algebraically. It's just those couple of rules you need to nail down.
Wow, okay, we've actually covered a lot of ground there. Geometry, coordinate geometry, trig, radians, complex numbers.
Yep. That's the full set of additional topics from Chapter 19. We went from concrete shapes to plotting them on grids to angle relationships and even into the imaginary realm.
It really shows how different areas of math connect, doesn't it? Like seeing right triangles pop up in geometry, coordinate geometry, and trigonometry problems.
Absolutely. They build on each other. Understanding these connections gives you a much deeper grasp.
So just to confirm for everyone listening, we have covered all the key skills, the strategies, the question types, those official examples, and the tips from Chapter 19 of the SAT Study Guide. We didn't skip anything.
Correct. This deep dive gives you the complete picture of what's in that chapter and what you need to focus on for test day regarding these topics.
Excellent. So as we wrap up, maybe a final thought for you, our listener, to mull over. How could the problem-solving skills we talked about today, like breaking down complex shapes, or using systematic methods like completing the square, or using conjugates, how might those approaches apply to other challenges you face? Not just on the SAT, but, in life.
That's a great question. That ability to break down complexity and apply rules systematically is pretty universal.
Something to think about.
Well, thank you for joining us for this deep dive into SAT Math's additional topics. We hope this focused look helps you feel more prepared and confident.